Now we will move on to last lecture, and the title is Simulation of Beam Transmission through an RF Resonating Structure, and it will be delivered by Mrs.Kumud Singh from BRC.
So first of all, I would like to thank Professor Kulkarni for giving us the opportunity to give the talk. And I had been the luckiest of all to have appeared on stage twice. One was my original talk, this was the planned talk. And yesterday I gave in replacement of my colleague who was busy with some other urgent work at the organization. So I would also like to appreciate the way he has been able to couple all the speakers, from the experts to research speakers to industry participants. So this EM workshop in practical sense has been taken as a coupled approach. So it has addressed the problem of students also, how difficult they find to relate with the EM theory. Then problem of teachers also, they are also struggling day and night to explain to the students application of this theory and what this theory has is related to the real life problem. Even researchers and the industry speakers also could tell what are the applications fields in which EM theory applies, apart from other applications which students have been studying over the years. So like yesterday,
Sentiment is reflected by number of participants. We don't
okay.
get so many participants for
Yes.
electromagnetic.
So there is a wide variety of participants as well as the speakers also. So this talk is not a tutorial, it's a case study. It will be a case study. So just I would like to read one quote, that education is not filling up of a bucket, it's lighting of a fire. But that doesn't mean the bucket should be empty. So there has to be a mix of the equation basis EM theory and the real life problems where you apply your EM theory. So through this case study, we will go through an interesting area where the EM theory applies. So this is a typical resonating structure. It's a klystron. Like yesterday we saw, klystron is an RF amplifier. So in more basic, klystron consists of 3 cavities. First, of course, is an electron gun, resonant circuit, and a collector to collect the beam. So it's related to the accelerator. In accelerator, what we do, we transfer the stored energy of the cavity to the beam. So that beam takes energy and hits on a high Z target. In the klystron, it's just opposite of an accelerator. This beam gives power. It modulates and demodulates and give powers to the RF cavity. We take out in the we couple the RF power through, we derive the RF power through beam transmission. So it consists of, first we derive electron beams from the cathode gun. Then once it enters the cavities, if in simple terms, I explain 3 cavity system. In various applications, there are 5 cavities, 4 cavities, klystron cavities to increase the gain. So in the first cavity, as the beam enters, if we take a simple sinusoid, this is an RF cycle. So if suppose whatever portion of the beam, there is a continuous beam entering into the first cavity. So whatever beam entering in the positive phase of the RF cycle will get accelerated, and this negative cycle beam will get deaccelerated. So if I go to the next cavity, what happens? This accelerated beam from the first cycle gets merged with the deaccelerated beam of the second cycle. So if I see, this velocity modulation gives rise to a current modulation. In the second cavity, we'll be having bunch of electron beams from the previous RF cycles and from the current RF cycles. So cavity by cavity, this current modulation keeps on increasing. So and in turn, this current modulation, it generates through mirror effects, it modulates the fields, RF fields in the intermediate cavities, which enhances the velocity modulation and it enhances the current modulation in terms. So that's why when we go to the output cavity, this increased current modulation will be demodulated. The third cavities will be designed in such a way so that this through coupling, through waveguide coupling or other coupling methods, we can take out this beam, that current modulation, whatever energy content is there in the beam, that can be derived from the output cavity. So this beam modulation is reflected in the fields which gets coupled to the waveguide, and we take out the RF power. So this is the simple phenomena which takes place in a klystron. So application wise, why I'm talking is because actually we have been associated with the development of a J-bond Klystron tube, which will be integrated into transmitter for a seeker missile application. My previous speaker, Professor Jalil Akhtar, was talking about active radar seeking. So this is one of the applications where this transmitters will be used. So what is a challenge in this? Challenge is in this frequency band, the dimensions are so small, and so as to, if you want to accelerate a high current beam, you will have to contain that beam in a very small dimensions. For this, only the drift part is 1 mm, through which the beam has to pass. That means beam size has to be 0.6 mm. So, and the current is of the order of 240 milliampere. The current density is quite high. So, space charge effects. Space charge effects are, if we see, there is a bunch of particles. There are electron beam or a proton beam. There will be Coulomb repulsions between the particles. So, there will be inherent electrostatic forces as well as magnetostatic forces. So, we call that as space charge effects. So, we have to balance the space charge effects so as the beam is entering from the electron gun, it retains its size, gives powers to the output cavity and gets collected at the collector beam. It should not collect at the cavity walls. So, that will give rise to beam loss. So, we want to minimize the beam losses. So, this, in simple terms, I will explain electron beam dynamics. Is if we see, this is the electron beam which is coming out from the electron gun, and at this point, when it is entering the RF cavity region, requirement is that magnetic field should be of the magnitude so that it just balances the space charge forces. So that beam is through electrostatic focusing, it's coming till this point, and then we have to apply magnetostatic forces. So in presence of RF fields also gives rise to some demodulation in the beam. So here requirement is just to balance the space charge effects of the beam. But that condition is called Brillouin flow focusing, where magnetic field is required just to balance the space charge forces. But in ideal conditions, we have demodulations due to RF fields. Then there are, at this dimension level, there even a slight misalignment can cause damage to the circuit. So we cannot work with the ideal conditions. It is an ideal condition. So we have to slightly go for a higher field, 2 to 2.5 times of the Brillouin field value, which disadvantage is that magnetic circuit becomes larger. But here in the Brillouin flow, there is no field is allowed in the cathode gun region. Cathode gun is only directed by the electrostatic forces, and then after this we take the magnetostatic forces. But in the confined flow region, there is a deliberate leakage of magnetic flux which is allowed in the cathode gun region, and this directions and the magnitude of the magnetic field is very important for the beam characteristics.
That will also depend on anode
voltage. Magnetostatic forces.
No, I mean that space charge effect which you are balancing.
Yes.
That also depends on anode voltage.
Acceleration level, at what? Yes, it depends on the accelerating voltages. It depends on the current of the beam and as well as the accelerating voltage. So this just explains the conditions of the Brillouin flow. These are all the ideal conditions. If we see, beam must enter the focusing region exactly parallel to the axis. That means there are no chances for misalignment. Then beam cross section must have a uniform charge density, again an ideal condition, because if we see cathode gun design, there will be some inherent limitations of the cathode gun, so that we will not be able to extract a uniform current from the gun. There should be no radial component of electron velocity. That is not possible because we are applying an electrostatic force to confine the beam. Magnetic field value must be exactly equal to Brillouin field. This is the Brillouin field value. This is depending on the current as well as the voltage. Then gun axis must be coincident with the magnetic axis. Beam must enter uniform at the equilibrium radius. So if we see, suppose beam is entering at this point field is just sufficient to balance the space charge forces. So beam will try to slightly diverge out, but at this point field value is more. As no, this A point. If we see, this two lines are where the magnetic field just balances the space charge force. So when the beam comes through electrostatic focusing, its size is slightly smaller. So here the magnetic field value is slightly less to balance the space charge forces. So at this point, beam will try to diverge, and as it enters this point, again the field balances the space charge effects. So again the diverging beam will come back, try to converge because of the magnetic field. So these are the perturbations which will be happening in the beam. So if we see beam size dependency on the current density, this is 1:1. If your brilliant, this is the ideal condition, brilliant field. So if there will be a change in the current density, it's linearly, beam diameter will linearly change. But that we cannot allow because of RF demodulation, there will be definitely change in the current density. So that's why we go for a confinement factor. That is the factor by which we are increasing the brilliancy. If we see it's m is equal to 2, there is this slope value, and this is at m is equal to 3. That's why we go for a higher field value. So this is the requirement of the magnetic field in the gun. This is the gun region, RF section, and the collector. So in the gun region, if we see, field is required is the order of 60 to 100 Gauss, and in the RF region it's directly jumps to 3500 Gauss. So it's huge rise. This rise is also very important to allow the beam enter in the drift tube region to get the ideal characteristic, to extract the beam power. So beam stick tube, when we start with the design, what we do, we don't complicate the design. What we do, we first only study the beam transmission. That means there are no RF perturbations, no RF waveguides, only resonant cavities, gun, and the collector region. We whatever in the design from beam dynamics, whatever field value we have got, we apply that field value and check whether beam transmissions we are getting is 90%, 99%, or it's less than that, just to check the magnetic circuit. So in this design, the beam current was around 240 milliampere, beam energy is 6 kilo electron volt, beam aperture is 0.8, beam fill factor is 65 to 75%. Beam fill factor is means how much of the aperture you are filling it with beam. It's 65 to 70% of the 0.8 mm. So we start with the electrostatic design of the cathode gun, because once if you are designing a magnetic circuit, you need to know the beam parameters also, how the magnetic field is affecting the beam. So we start with the electrostatic design of the cathode gun, and we in the simulation we find out at what point what is the beam size, total current, for which we have to apply magnetic forces. Then electromagnetic design of the focusing lenses. This was the circular symmetry for the ideal condition where we are applying a beam stick tube. But once this was the permanent magnet design and the electromagnet design, and whatever was the requirement in simulation, we could achieve what was the requirement, equal to the requirement. This was the permanent magnet and the electromagnet. Electromagnet has flexibility that you can tune the magnetic field. You can change the current and tune the magnetic field. But permanent magnet has only got the discrete tunability. You can remove some of the magnets, and in maybe 200 steps of 200 Gauss, you can change the magnetic field. So this was then next came once the beam transmission through beam stick tube we were able to extract. Then came the complication of the RF waveguides. There are RF waveguide ports where we cannot allow any magnetic component to sit. So we had reduced magnetic volume, but still the requirement of the magnetic field was same. So there was some optimization studies carried out for the pole design, shield dimensions also, to get the same field parameters as desired. Such as these all are done through a commercial software, Opera, from Vector Fields. So that's why here also that that academicians can collaborate with the researchers to write good FEM codes, so that we can find a replacement for the important version of the codes. We can start with simple problems and then go on inserting the parameters or optimizations and all that. So this was again that all field that arrow plots we ensure that arrows field directions and the magnitude is optimized in the gun region as well as in the RF region. So this is the optimization studies. In the dimensional term, we optimize the outer dimension of the shield, then the chamfer angles also, and this shield length also, which decided what is the level of the field at the cathode gun. So this parameterization was done taking one parameter at a time, and then at the end solving, taking all the parameters in account. And then tracking of the charge particle beam in the magnetic field. These are the two inherent pole pieces of the tube, where we have to retrofit the external magnetic circuits. So if we see, this is the beam coming from the, here we have assumed a parallel beam, but it's not actually in the case. It's coming, if we see its dependence on the magnetic field value at 1600 Gauss, which is the brilliant field value for this current, 240 milliampere and 6 kilo electron volt. So the beam size, if we see, it's almost same, 0.4 beam if we are entering, in the drift tube aperture we have 0.4. If the beam enters 1 mm, in the drift tube aperture also it's beam of 1 mm. So this is R versus Z, same, we see X is Z. And as we increase the this field value, at 2200 Gauss and 3500 Gauss, which was the actually desired, we see actually there is a 50% reduction in the beam size. So if suppose 65 to 75% of the beam filling factor is required, so we can calculate by that what should be the beam size entering at the cathode gun region and the field level which is required in the RF cavity region. So this is just after electrostatic design, electromagnetic design, and what we do is by solid modeling we try to integrate the components, how we'll be assembling with the tubes, because this tube is actually a very delicate, because it's having a ceramic seals, and any mishandling during the assembly can damage the tube totally. So this sprocket was inserted from the top, and this pole pieces were slide from the sides so that it exactly goes and fits into the inherent pole pieces. This was again a retrofitting of the PM lens to the miniature Klystron tube, where again we inserted shields, soft iron parts were brought in two halves, tube was inserted, then magnets were brought together after the shields were locked in place, otherwise then shields would fly off. So if we see fabricated focusing lens assemblies, after electrostatic electromagnetic design, coupled analysis, and the integration in the solid modeling, after that we fabricate the assembly and check for its mechanical integrity and all that. And then after this, very important step is the measurement. Whatever by simulation you have got, whether in practical conditions you are able to achieve that or not. If there are some manufacturing errors which creep into your magnetic field, that would be detrimental. So after that we map the magnetic field. After the design, we map the magnetic field through the bore of the magnet, and we were able to match the simulated and the measured B field. So on axis and off axis measurements have been carried out. So if we see, these are the beam transmission trials which were carried out at CV Pilani. After we integrated actually this tube is very small, it's of a size of a palm. So we see this is the magnet and this is the tube. These are the vacuum pump and sputter pump for maintaining the vacuum in this tube. So this tube has been pinched off after its vacuum processing, and this is for residual vacuum, we are having a pump. So this is the electromagnetic lens. So what we were able to achieve is, this is the beam stick tube where we have a continuous electromagnetic we could enter, but that is not possible in the miniature Klystron tube because there are waveguide ports for that. So we were able to achieve 90% of the transmission. That means whatever 90% of the beam emitted from the cathode gun, we were able to collect at the collector. So after the beam transmission trials, we went to the RF trials. So in the RF trials, that other magnet design was taken where we were having spaces for the waveguide openings. So we were able to extract up to 127 watt of power. So this is the first time in India which we have been able to extract this much power from this size of the tube. So still we are working on this design, and we are improving so that we can increase the RF power level. Frequency is 17 to 18 gigahertz, in the band of 17 to 18 gigahertz.
Let's thank Miss Singh, Mrs. Singh. Okay.
Can you explain how you produce that work?
By magnets.
Yeah.
So in the beam stick tube, what we have done is we have taken an axially magnetized magnets, and we have created an aluminum sprocket, and we have arranged this axially magnet. If I see in this view, this is the beam line. These are the axially magnetized magnets. Then here all shapes we have tried to optimize so as to direct these field lines in the cavity. Similarly, in the miniature Klystron also, magnets are from two sides also. It's not 360 degrees, but still pole shape we have kept optimized so the field inside the RF cavity is uniform.
So let's thank Mrs. Singh for nice presentation. You can. With this, then we come to end of this session. I thank Professor Kulkarni for organizing such a workshop, and I compliment him to have such a large number in this field. So thank you.
So thank you, Dr. Ray, for chairing this session. And I don't know whether he introduced himself. He is an acknowledged expert in India, on microwaves and radars, and he has developed many instruments and systems which are of national importance. So with this, I think we come to an end of this 2 days so-called a very hectic workshop. We can formally close this workshop, and thanks. Particularly, I anyway gave vote of thanks in the inaugural thing, but again I would like to thank all those who contributed for making this workshop successful. Be it invited speakers who came all the way from various places, be it participants who came here with the sole purpose of learning electromagnetics. So I think we all together have made this workshop successful. Thank you very much, and enjoy the dinner.